Welcome to part 3 of our Introduction to Significance test. This is going to cover one-sided versus two-sided tests and how the alpha can affect your conclusions. Let's suppose you ran a test of P with a sample proportion of P hat equals 66 out of 96, which is 0.69, in the following hypotheses. So hypothesis 1, we have our P equal 0.6 and P is greater than 0.6. 2, P equal 0.6, P is less than 0.6. Notice that that's a large chunk there. We wouldn't really want to do this one in practice. Hypothesis 3, P is equal to 0.6 and P is not equal to 0.6. Look what happened to our normal distribution. Notice it's covering both sides here versus this side, which is just 1. So we can verify that the standard error is going to be about 5%, 0.05, and our z-score is positive 1.8. I'm not going to do that here, but let's do a couple calculations. First, what's the p-value for hypothesis 1? So let's look at our p-value here. Our z-score is 1.8, and we're going to calculate the probability of getting 1.8 or more extreme in a normal curve. Well, that's going to give you a z-score or a probability of 0.0359. What's that conclusion going to be then? Well, since we're comparing it to 5%, it's less than 5%, we're going to reject the null. What if it was a 1% alpha? Then we would fail to reject it because that number is greater than 1%. Now, for this one here, well, if we're following the hypothesis, it's less than, and our upper bound would be 1.8 in this case. But we wouldn't want to do this because this is going to be 96.41%. It's actually 1 minus our previous probability. Why would it make sense not to do this? Well, that sample's in the wrong direction of the alternative hypothesis. Notice that our sample size, our sample proportion was 69%, but the alternative is saying go less than that. Well, that would not make sense to have a sample up here, but have alternative be less than 60%. Doesn't make sense. So we wouldn't do that in practice. Let's look at hypothesis 3. Now, what's the p-value when I have a not equal to? Well, it's going to be our first one, but it's going to be doubled. So remember, we got about 3.59% for just greater than 1.8 as a z-score. So if I double that, it's going to be 0.0719. So it's going to be the left and the right side of that normal curve. What's our conclusion going to be for alpha is 0.05 and alpha is 0.01? Well, in this case here, that p-value is going to be greater than both. So we're going to fail to reject it. We don't have enough evidence to overturn those results and conclude the alternative here. So the takeaway here is that you got to have some evidence to be able to run this test. Otherwise, you're going to be wasting your time. We don't want to be doing this because it's not going to make any sense to run a test when your sample is above in the wrong direction of the alternative. So we have to have evidence. And then we also, when we're calculating for a two-sided test, it's going to be double the p-value of a one-sided test. And never change your alpha after you run a test. Always have that predetermined. If you're not given one, use 5%. So let's look at example 4. According to the National Center for Health Statistics, 36.6% of U.S. adults eat fast food on a given day. That's going to be your null right there. That's what we're given here. Part A, a public health director wants to know if this figure is more for adult residents of a particular county. A random sample of 150 adult residents from this county finds that 66 residents ate fast food on a previous day. So 66 out of 150. Set up appropriate hypotheses, calculate a test statistic and a p-value, assuming the conditions are met. So we don't have to check them in this case here. Part B, what conclusion would you make? At the 5% value, how would this change if it was 1%? Part C, suppose the public health director wants to know if this figure is different for adult residents of the same county using the same sample. What is the p-value? Assume the conditions for inference are met. And finally, what conclusion would the health director make based on the p-value at both the 5% and the 1% levels? Let's get to it. So part A, we have a random sample of 66 residents. And we want to calculate hypotheses, calculate a test statistic, and a p-value. Let's start with the hypotheses. Got your hoe and your hot. All right, the null hypothesis is coming from the original claim, 36.6%. We want to write that as a decimal and use p, not p hat, because we use our parameter. Our alternative, in this case here, a public health director wants to know if the figure is more. That's greater than, y'all. So p is greater than 0.366. So I'm not going to define this, but let's go ahead and calculate our test statistic. To calculate our test statistic, we're going to need our sample proportion. So we have 66 out of 150. So we calculate that, we divide those out, and we're going to get our sample proportion, which is going to be a 0.44. Let's talk about our test statistic. Remember, it's z equals, and we always do our sample minus our null. So remember, this is going to be your p hat. This is going to be your p, your null. And then down here, remember, we do our standard error formula, but we do it based on the null. And our number in the sample is 150. So that's going to look like this. 0.366 parentheses 1 minus 0.366 over 150, all under the square root. Very carefully calculate that number. That's your z score. That's your test statistic. You're going to get 1.88. 1.881, I think, is what I rounded to. So let's talk about getting our p-value from there. Remember, this is based on the normal curve. It's a z-score. We have a positive z-score. So if I'm going to go to second vars, I'm going to go to normal CDF, but my lower bound in this case is going to be the 1.881. We want to go to infinity in this case since we're going in the positive direction, since it's greater than. Leave it at 0 and 1, and you'll get a p-value of about 3%, 0.0299. You don't have to show work for that. This is assume that you know how to use table A or your normal CDF for z-scores. So you write the probability z is greater than 1.1881 is equal to 0.03. That's your p-value. Now it says assume the conditions are met. We don't have to check those here, so we're off the hook. Let's go to part B. What's your conclusion going to be? Well, our p-value was about 3%. So how would this affect our conclusion? Remember your conclusion template. Small p-value, reject the hoe. When the p is low, reject the hoe. We have convincing evidence. When the p is large, we fail to reject the hoe. We do not have convincing evidence. So in this case, our p-value is 0.03. It's not large. In fact, when alpha is 5%, we're going to reject that null hypothesis. There is convincing evidence for the alternative. When alpha is 1%, however, if you set that at 1%, we're going to fail to reject the null hypothesis since it's not less than 1, since your p-value is not less than your alpha. In this case, there is not convincing evidence for the alternative. Part C. Suppose the public health director wants to know if this figure is different for adult residents of the same county using the same sample. In this case, what's the p-value? Assume the conditions for inference are met. So remember, different. Different means, what does that mean? That means the alternative is not equal to. Not equal. Different isn't above or below. It's not equal to. So what do we do in this case? Well, we go in the extreme direction for both the positive and negative z-score. So we had 1.881. That's your z-score here. And then this one is the probability of z is less than negative 1.881. But this is perfectly symmetric. It's a normal distribution. So whatever this is, it's going to be the same thing over here. So all we have to do is take our p-value from our first part and double that. So that's going to be about 6%. Now, what's that going to do for our conclusion? If we were to do a not equal, a two-sided test, in this case here, that 6% is greater than both 5% and 1%. So we would fail to reject that at both levels. We would not have enough convincing evidence to overturn the alternative. All right, let's check your understanding. Pause this video and try it on your own, please. going to read through it. So according to the National Institute for Occupational Health and Safety, job stress poses a major threat to the health of workers. A news report claims that 75% of the restaurant employees feel that work stress has a negative impact on their personal lives. The board of directors of a restaurant chain with thousands of employees wonder whether the claim is true for their employees. A random sample of 100 employees finds that 68 answer yes when asked, does work stress have a negative impact on your personal life? Part A. State the hypotheses the board is interested in testing. Be sure to define the parameter of interest. Part B. Check the conditions for a test about the population proportion. Part C. Calculate the standardized test statistic and the p-value. Part D. What conclusions should the board make? I'll leave you to pause this and try this on your own. And we're going to go over in 3, 2, 1. So the hypotheses. This is a proportion. So 75% was the claim. P equals 0.75 would be your null. Your alternative, the board of directors at a restaurant chain with thousands of employees wonders whether the claim is true. That's a not equal to. It's not a less than, it's not a greater than. It's simply a not equal to. So P is not equal to 0.0575. It says be sure to define the parameter. So P is the true proportion of restaurant employees who feel work stress has a negative impact on their lives. Part B, check the conditions for a test. So the conditions, random sample of 100 employees, which is less than 10% of the employees at this chain that says has thousands of people. And finally, our normal large counts. Remember, we use our null, not our sample, so we use our 75% and our 25% using our sample size of 100. Both of those numbers, 75 and 25, are greater than or equal to 10. So we've checked our conditions are met. Now we can calculate our standardized test statistic, our z-score. So our sample proportion is what we need to be able to do this. So that's 0.68, 60 out of 100. And our z-score is going to be 0.68 minus 0.75 over the square root 0.75, 0.25 over 100. That's going to be that same test statistic that we use for all of these one proportion. All right, when you calculate that out, you get negative 1.617. Let's do a normal CDF. So you're going to do normal CDF. Z is less than negative 1.617. Now you might say, well, why less than? Why not greater than? We go in the more extreme direction. So if it's a negative z-score, we have to go less than that number. So we want our small number to be negative infinity. We always want our negative number to be the upper bound in a normal curve if we're going in the more extreme direction. So that's your 5.29%. You can round that to 5.3% if you want. But in this case, remember that the alternative hypothesis was not equal to. Since this was a two-sided test, we're going to have to double that value. So it's actually about 10.59%. So if you go into your calculator and you do this calculation, you click times 2, that'll be the actual p-value for here. It's going to be about 10.6%. What's our conclusion? That's a very high p-value. So it's not unusually small. We're going to fail to reject the null hypothesis. There's not convincing evidence to overturn the 75% claim. All right, let's do a little lesson summary. Going back to the beginning from the first video, remember our hypotheses, you always have a null. It's always going to be a parameter, so it might be p or mu. For the next couple lessons, it'll be p. And our alternative will always be either less than, greater than, or not equal to if it's a two-sided. Always define your parameter in context of the problem. The p-value, remember we have to have an alpha level set, so typically it's 5%, but the p-value is the likelihood, the probability of getting evidence for the alternative that is as strong or stronger than the observed evidence when the null is true. And we have a little template for that. So I would memorize that template, assuming the blank. There is a blank probability of getting a sample blank, a blank, or blank by chance alone in a random sample of blank. It's a mouthful, but if you write it enough, you'll get it. Remember, when the P is low, reject the hoe. We have convincing evidence in context. When the P is high, we fail to reject it. There's not convincing evidence in context. Never say we accept the null hypothesis. We either reject it or we fail. And finally, just a couple calculations to help remember. This formula here is not on your formula sheet. The standard error one is, and the generic standardized test statistic is. So remember how to use it. In the next lesson, I'll show you how to use your calculator test menu to get this value. For right now, play around with it. Use the formulas to help. Remember, for a one-sided test, you always go in the more extreme direction. So if it's a positive z-score, you go above it. If it's a negative, you go below it. And if it's two-sided, go in the more extreme direction, depending on what you're given, and double that p-value if it's a not equal to for your alternative. Y'all, thank you for watching. This was a long lesson, and I appreciate your patience with me. Have a great day.